Welcome to the second part of this series, where we'll look into addition and subtraction of matrices using this question as gotten from our intro video. And our required matrices A and B are given as follows. Now, there is a major rule to note when dealing with these concepts. Let's take a look at this matrix. It has two rows going from left to right and two columns going from top to bottom. So we call it a 2 by 2 matrix, written as 2 times 2. This is its dimension. Now, a 2 by 2 matrix can and should only be added to or subtracted from another 2 by 2 matrix. It should not and actually cannot be added to or subtracted from a matrix with any other dimension. So at this point, we can conclude that only matrices with the same dimensions can be added or subtracted. And going by that, when we take a much closer look at our question, we'll realize that the question right here is basically asking us to add a 2 by 2 matrix to a 3 by 3 matrix, which is not possible. So that eliminates this question from our list. Then you will notice for the other two questions, we'll have the letter I linked to them. So what is I? Well, I is what we refer to as the identity matrix. And this identity matrix can be represented in two forms, as a 2 by 2 matrix or a 3 by 3 matrix. The 2 by 2 identity matrix consists of only zeros and ones, as seen here, and the same goes for the 3 by 3 identity matrix. This may look a bit difficult to memorize, but when you remember that 1 cuts across diagonally for the 2 by 2 matrix and the 3 by 3 matrix, it should be easier to remember. Now, how can you tell when to use a 2 by 2 identity matrix or a 3 by 3 identity matrix? It's easy. When the question is linked to a 2 by 2 matrix, we use a 2 by 2 identity matrix. And when the question is linked to a 3 by 3 matrix, we use a 3 by 3 identity matrix. Let's see our first question, A plus 3i. We write down matrix A, which is a 2 by 2 matrix, then the plus sign. Now, 3i represents scalar multiplication, which we express mathematically by putting down matrix I, in this case in its 2 by 2 form, since it is linked to A, which is a 2 by 2 matrix. Then we place 3 before it like this. We perform the scalar multiplication by multiplying all the elements in the identity matrix by 3 like this, and we bring these down. We should arrive at this for 3i. We can then add it to A to get something like this. Now, how we arrive at this is very easy. We obtained the first element of the first row in our answer by adding the very first element on the first row in both matrices above. We obtained the second element on the first row in our answer by adding the second element on the first row in both matrices above. We obtained the first element on the second row in our answer by adding the first element on the second row in both matrices above. Finally, we got the second element of the second row by adding the second element on the second row in both matrices above. So we can see that basically it's all about position. So this leads us to our final answer as this. For B minus 2i, we do the same thing. We first of all write down the matrices for B minus 2i. You'll notice that in this case, our identity matrix is the 3 by 3 identity matrix form. And this is because the question is linked to B, which is also a 3 by 3 matrix. Then we multiply all the elements in the identity matrix by 2 to get something like this. Then we bring this down. The scalar multiplication should result in this. And when we subtract, we should arrive at this. And the method remains the same because it's all about position. Let's take some random samples. 0 minus 0, which is the second element on the first row, was gotten by subtracting the second element of the first row in both matrices above. Minus 6 minus 0, which is the first element on the second row, was gotten by subtracting the first element on the second row in both matrices above. Minus 1 minus 2, which is the third element on the third row, was gotten by subtracting the third element on the third row in both matrices above. and the same goes for all the others. So all these leads to our final answer as shown here.